All right, so let's get into 9.2, where we're talking about solving oblique triangles, where we're going to be using the law of sines primarily to find the missing sides and the missing angles. So there are two scenarios, or two primary scenarios, where you use the law of sines based on the information that's given. The first scenario is going to be angle, side, angle, which is effectively the same thing as angle, angle, side, or side, side, angle. And the other scenario will be side, side, angle, and we'll get into that second situation a little bit later. So here is the law of sines. Sine of angle A over side A equals sine of angle B over side B equals sine of angle C over side C. And that applies for any triangle that can be labeled as such. And keep in mind that the lowercase letters represent your side lengths, whereas your capital letters will represent your angle measures. And of course, the letter of the side length is always going to be across from the angle. So your angles are always across from your sides that they produce, and you always have the letters that are going to be across from each other. So you have angle B across from side B, angle C across from side C, angle A across from side A. So now let's begin to use the law of sines formula to solve the triangle. And remember, whenever you solve a triangle, that simply means to find all of the missing sides and all of the missing angles. So we have two angles that are given, so we can use that information to find the third angle first. So we have angle, this angle looks like this would be C. So this angle measures 10 degrees. Angle A is 110 degrees. 10 plus 110 is 120. So that means angle B is the remaining 60 degrees in the triangle, because all three angles should add up to be 180 degrees. So if you add 60 plus 10, that gives you 70, plus 110, that gives you 180. So angle B is correct at 60 degrees. Now we need to find side B and side A. So we'll use side C and angle C to begin with. So sine of angle C, which is 10, over side C, which is 1, is going to be equal to sine of angle A, which is 110 degrees, over side A. And now we need to simply solve this formula for A to get side A. So you can cross multiply. So you have A sine 10 equals sine of 110, and then you simply need to divide both sides to get A by itself. So you'll have A equals sine of 110 divided by sine of 10, which is approximately, let's do sine 110 divided by sine of 10, and again, make sure you have it in degrees mode if you're using degrees as your angle measure. So side A is going to be 5.41. So 5.41 for side A. And now we do the same thing, but this time we use angle B, and we're solving for side B. So same thing. We're going to use sine of 10 over 1, which was angle C and side C, equals sine of 60 over B. So then B will equal sine 60 over sine of 10. So now we're doing sine of 60 divided by sine of 10, and that gives us 4.99. So side B is going to be approximately 4.99. Now we have all of our missing sides and missing angles, so this triangle has been solved. For number 2, it requires us to use the same solving method. We just need to draw the triangle first based on the dimensions that are given. So it says angle A is 10, angle B is 35 degrees, and side C is 5 units. So we can draw any arbitrary triangle. So we can label this as angle A. This will be 10 degrees. Angle B can be here. It doesn't matter which order we label them in, as long as we put the corresponding letters in the correct place. So if this is angle A, then across from angle A will be side A. And if this is angle B at 35 degrees, then across from angle B will be side B. And this will be side C, which equals 5. So this will be angle C. So now we can use the angles that we know to find our missing angle. So this is 10, this is 35, so 45. So 180 minus 45 will be our remaining angle. So this will be 135 for angle C. So now we can use angle C and side C to start us off again. So sine of 135 will equal sine of 30, over 5. This will be over 5 because this is sine of C over C, and that equals sine of 35 over B. And then likewise, we're going to solve the same equation, but for side A. So sine of 135 over 5 will equal sine of 10 over side A. And then we solve it just like we did over here. All right, so now is where it gets to be a little bit more interesting when you have the ambiguous case scenarios, when you have side-side angle situations, where you're given two sides and then an angle that goes across from one of the sides. Then you're in your side-side angle situation, and you are going to have a different scenarios depending on the information that's given. So the definition of ambiguous is here. That means it's open to more than one interpretation or having multiple meanings. If you have two sides and the non-included angle that's given, you're going to have these three possible situations. So if you have a triangle like this and you label it as such, if side A is longer than the other side times sine of A, then it's shorter. Sorry, if it's less than, then you have no solution. If B sine A is less than side A and is less than, which is going to be less than side B, then you'll have two solutions. Otherwise, if side A is longer than side B, then you're only going to have one solution. So it's easiest to just check if you have the one solution situation first and then move on and do the comparisons later. So let's look at some of these examples to make sense of it all. So we have angle C, we have side B, and we have side C. So since C is the side who has its angle that's going along with it, we first check to see is that side also longer than the other side. It is longer than the other side, so then that means we're going to be in a situation where we have one solution. So in this case, the C took the place of A. So basically you're comparing if the side who has the angle to go along with it is the longest side. If it is, then you have one solution. So C is longer than B, in this case, C being the side that has the angle to go along with it. So we have one solution here. Now, looking at B, we have angle B that's given. So we look at side B, but in this case, it's less than side A. So now we also need to plug it in to make a comparison to see if A times sine of B, in this case, is going to be longer or shorter than the other side. So we're going to have to do 27 times sine of 33 to see if that's going to be longer than 22. If it is longer than 22, we have no solution because it's going to be too long. So 27 sine 33 is 14.71. So in this case, it's shorter, so we're going to have two solutions. Now we're looking at C. So C says B equals 35. They give us angle B. So we look to see, is side B longer than the other side? It's not, so then we need to do the comparison. So we do 24 sine 35 to see now, is this going to be longer or shorter than this side? If it's longer, then it goes beyond this side and we won't have a triangle in this case. So let's see, 24 sine 35 is 13.77. And this is longer than side B. So in this case, it'll be no solution, because it is 13.77. And now finally, let's look at D. D says A equals 29 degrees, side A is 17. Side A is shorter than side C, so then we need to check. If side A was longer than side C, then we would have just been in a one solution situation, but it's shorter than side C, so now we need to check. So we do C times sine of A, so 18 sine of the angle, 18 sine 29, and this gives us 8.73. And since 8.73 is shorter than side A, that's going to be another case where we have two solutions. So now, what we started out on our first side, remember we are talking about solving these triangles. So now we need to continue to say what we do in these three cases. Well, obviously, in case one where there's no solution, then there's nothing else you can do. If it's one solution, then you just finish solving the triangles using the law of sines, like we did before in our previous examples. If there is a case where there's two solutions, then we need to do a little bit more work, because there's actually two possible triangles that we could be solving for. So first you want to find the missing angle, and this is done using the law of sines. So you find that missing angle using the law of sines, and you find the supplement of that angle. The supplement of that angle will be the angle in the second triangle. So we'll create another triangle in the case where we have two solutions. One of them, they'll both be labeled with the same given information, but the missing angle that we find is going to be where they begin to differ. So you use one triangle with the missing angle that you find in the beginning, then you find the supplement of it and you label that on the second triangle. And then once you have those two angles, you just finish solving using the law of sines. So let's look at an example where this happens. So we have side B, side C, and angle B. So let's draw our first triangle. So side B is 8, angle B is 30, side C is 9. So we have another side angle situation. So let's see how this one works out, whether or not we get one or two or no solutions. So we're going to do 9 sine 30, and we'll see, is that going to be greater or less than 8? So 9 sine 30 is 4.5, which is less than 8. So we have another case where we have two solutions. So again, first we want to find our missing angle. So we'll find this angle that's across from 9. So we do that by using the law of sines again. So we'll have sine of 30 over 8 equals sine of C, because this is across from side C, over 9. So now we're solving for angle C. So we're going to cross multiply. We'll have 9 sine 30 equals 8 sine C. and then we need to divide both sides by 8. So we have 9 sine 30 divided by 8 equals sine of C. And then to solve it from here, we need to do the inverse of sine around all of this. So what we're going to actually be plugging in to get angle C, I'll write it up here, C will be equal to sine inverse of 9 sine 30 over 8. C equals sine inverse of 9 sine 30 divided by 8. And that equals 34.22. So angle C in our first triangle that we started with is 34.2. Now we can find our other angle that's going to be up here by simply adding these two together and subtracting it from 180. So this would be 64.2. So 180 minus 64.2 is 115.8. So now we have all of our angles. We only need to find the other missing side using the law of sines again to find side A. We have our A here. So now, remember again, like we said, this is only one possible triangle. So we can say, actually, this is just C1 for our first triangle. So this will be C1. In our second triangle, we're going to find the complement of this angle. So we'll still have, and of course it's not going to be drawn to scale, but we still have 30 here. B is still 8, C is still 9. But angle C, this we'll call C2, is going to be different in this triangle. So we'll find the complement of 34.2. We do 180, the supplement, we do 180 minus 34.2, and this is C2. It's going to be 34. It's going to be 145.8. So this is 145.8, and now we can find angle A. 145.8 plus 30, 180 minus. So we get 4.2. So this angle is going to be little bitty 4.2. And obviously the figure is not drawn to scale, but these are the correct number value. So this is C2, so this is A2 in our second triangle. This is still B. B and C are not going to change. Side B and side C, that is. So then we will find side A again using the law of sines for the rest of it. So again, in your two triangles, you're going to compare. If you have a two solution situation, you find the first missing angle, and then you use the complement of that angle in your second triangle, and then you work out the rest of it using the law of sines. All right, so now looking at some of our application problems. The first one says Pat needs to determine the height of a tree before cutting it down to be sure that it would not fall on a nearby fence. The angle of elevation of the tree from one position is h equals 50, and from the second position, L is going to be 50 feet farther away, and that angle is 20 degrees. What's the height of the tree? If you remember from our last one, I advise you guys to always start by drawing a picture of the scenario to make sure that you can see everything that's going on. So the angle of the tree from one position is going to be 50 degrees. And then it says from a second position farther along the path. So this is going farther away from the tree. The angle becomes 20 degrees. So this is 20 degrees. And then it says, what is the height of the tree? So we're looking for the height of the tree. The first angle, the first position is 50 degrees. They said this was H. And then the second position, L, 50 feet farther along the path. That angle is 20 degrees. So now we're looking for the height of the tree. So we at least have one side and we got some angles that we can work with. So if this is 50 degrees, notice that this angle will be supplementary here. So we can do 180 minus 50 to get this angle measure, which is going to be 130 degrees. So now, again, we're still trying to get back to the height of this triangle. But we don't know anything about this smaller inside triangle here yet. So let's see if we can at least get one of these sides worked out. Notice that we have angles in this triangle and we have this side, which is 50. So we can use the law signs to at least find this distance in this triangle. So we have a triangle here and we're going to use the law sign. So we'll do, this is 50 and this is across from this angle up here. So this angle measure will be, let's see, 130 plus 20 is 150. So this angle measures 30 degrees. So we're doing sine of 30 degrees over 50 is going to equal sine of 20. And we'll just call this side, let's call it P, equals sine of 20 over P. And then once we know what this side is, we can, and this is actually a right triangle, so we can just use SOHCAHTOA to figure out what this vertical distance is on this triangle. So let's see, P is going to be 50 times sine 20 over sine of 30. So 50 sine 20 divided by sine 30. So this will equal or be approximately 34.2. So now we know the hypotenuse of this right triangle is 34.2. We have the angle and we are looking for the opposite side, so we can use sine again based on this right triangle here. So we'll say sine of 50 equals h, the opposite side, over P, which is our hypotenuse. We know for P we're going to be substituting 34.2. So H equals P sine 50. So here is still what we have stored for P. So we'll just do P times sine 50. And this gives us 26.2. So the height of the tree is approximately 26.2. All right, so the next one says Coast Guard Station Able is located L equals 140 miles south of Station Baker. So that means Baker is up above Station Able, 140 miles, and then Able is 140 miles south of Station Baker. A ship at sea sends an SOS call that is received by each station. The call to Station Able indicates that the ship is located north 55 degrees east. So this is just pure north, then it's going north and then 55 degrees out to the east. So this will be 55 degrees. And then the call to Station Baker indicates that the ship is located from Baker is south and then 60 degrees east. So you have a right triangle that looks something like this, where the ship is here. So here is our ship. So, and this is 60 degrees. So we can go ahead and label this angle just in case we need it later. This will be 115. So 180 minus 115. This is 65 degrees in case we need it later. It says this is how far is each station from the ship. So we're looking for side A and side B. And notice that the side A is going to be the distance from Baker to the ship, and side B is going to be the distance from Station Able to the ship. So we have this distance, 140, we have all of our angles, so we can use the law signs to find these distances. So sine of 55 degrees over side A equals sine of 65 degrees over 140. There we go. That's a better picture. So now we solve this. So A is going to be 140 sine 55 over sine 65. Likewise, for B, we'll do sine 60 over B equals sine 65 over 140. So B will equal 140 sine 60 over sine 65 over sine, over sine 65. Right. So now let's work these out. 140 sine 55 divided by sine 65 is going to equal 126.54. And then 140 sine 60 divided by sine 65 is going to be 133.78. So this is A, which is the distance from Baker. So this is Baker distance. And then this one is Able distance. So now it says if a helicopter is capable of flying 200 miles per hour and it dispatches from the nearest station, so that means it's going to be dispatched from Baker, how long is it going to take to reach the ship? So and on your problem set, it's asking for this time in minutes. So we're given 200 miles per hour, so we need to convert that to how fast it is traveling per minute. So if it travels 200 miles in 1 hour, you would have to do, you have 200 miles per hour, and we want to change that to miles per minute. So we have to do times, we put 1 hour at the top because our time is at the bottom. So we put minutes at the bottom. The hours will cancel, and 1 hour is 60 minutes. So we do 200 divided by 60 to get our speed in miles per minute. So 200 divided by 60, we get 3.3 miles per minute, and it's going to be traveling a distance of 126.54 miles. So we do that speed times 126.54 miles, and we get, we're supposed to divide. We have 126.54 divided by 3.3. And that gives us 37.96. So 37.96 minutes is how long it will take. All right, now we have an aircraft that's spotted by two observers who are 50 feet apart. As the airplane passes over the line joining them, each observer takes a sighting of the angle of elevation to the plane as indicated in the figure. Angle A equals 30 degrees and angle B equals 20 degrees. How high is the plane? So it's trying to ultimately get this height. So if we notice from our picture, we have a pair of right triangles that are back to back. We also have L being 1,050 feet apart, or the distance for L is 1,050. And we're looking for this vertical distance. So we notice that we have a larger triangle here, so we know this total angle measure to be, if this is 20 and this is 30, that's 50. So this big angle here, the Z, is going to be 130 degrees. So now we can use that to figure out one of the hypotenuses of these right triangles. And once we have one of the hypotenuses, then we can solve for this vertical distance. So we'll do sine of 130 over 1050. So sine of 130 over 1050 equals sine of 30 over this hypotenuse. So we'll call this side A since it's across from angle A. So then A equals 1050 sine 30 over sine of 130. So that gives us 685.34. And this is not our final answer. This is just side A. So side A is 685.34. So now we can use just this right triangle to figure out this height. So this would be the hypotenuse of this right triangle. This is our angle, and this h would be the opposite side, which is what we're looking for. So we'll say sine of 20 equals the opposite side h divided by 685.34. So then we multiply 685.34 times sine of 20, and that will give us h. And that is approximately 234.4. Number 4, we have a famous leaning tower that was originally 185 feet high. It's at a distance, and then it says at a distance of 121 feet from the base of the tower. The angle of elevation to the top of the tower is found to be 60 degrees. Find the perpendicular distance from the ground to the top of the tower. So we're going to be looking for this vertical distance here. Now, when we're looking for this vertical distance, we know this is a right angle here, just in this imaginary triangle that we draw now, but we don't have enough information about this triangle to just go ahead and jump right in. So first, let's solve for another angle in the triangle, which is going to be angle P here. So we're looking for RPQ. So the way that we'll find RPQ, we can do sine of 60 over 185.5. And actually, this is going to require us finding angle R first, because we don't know even what side P is. So we can use sine of R over 121, because we are given this side down here. So now we will multiply and use sine inverse to solve it. So we'll do sine inverse of 121 sine 60 divided by 185.5. And that will give us 34.4, it looks like. So angle R is approximately 34.4. So this full angle, 34.4. So that means this angle we can now find. So this is 60 plus 34.4. That gives us about 94.4. And then we'll do 180 minus that. And that gives us 85.6. So now we have angle RPQ, and we also have angle R. So now we can use this angle that we have in this right triangle over here. So we can do sine of 85.6 will equal our vertical distance divided by the hypotenuse of our triangle over here. So sine of 85.6 is going to equal the distance we're looking for, that vertical distance h, divided by 185.5, our hypotenuse. So we multiply h equals 185.5 sine 85.6. And that equals 184.95. So this is the perpendicular distance now. So it looks like it shrunk just only slightly, only from 185.5 to 184.95, so about a half a foot.